This week, we're getting into the scientific method, which is a rational means of attempting to conduct scientific inquiry. So when scientists have a particular identified problem or question that they are wanting to investigate, the scientific method helps provide a rational way of gathering data in a controlled environment that allows meaningful results that can not only be interpreted by the scientists and other members of the scientific community, but can be replicated by other scientists to see if their attempts at the same experiment bear out similar results that either lend weight toward a particular view that we would call a hypothesis or call into question that hypothesis. It takes repeated trials and often repeated refinement of particular approaches in scientific experimentation for the scientific community can feel like there is a valid, significant data set that does lend support or simply does not lend support to a particular hypothesis. So let's take a look at an example. In environmental science, pretty much half the textbooks you will ever see will love to do bird studies. Let's do a bird study with a fictional species called a purple wampler. I brought it up a few minutes ago. So a team spent 13 days observing purple wamplers in 3 different tree stand ages. In other words, 3 different areas of forest where one group was of a significantly different age since it was last cut than another group. All stand ages were roughly 20 acres in size. Each stand was part of the McHenry Memorial Forest. Fix that. Stand 1 was a recovering 50-year-old site with closed canopy, 100% closed, and an extensive mid-story. That means that all the trees that had started at the same time, 50 years before or after the previous forest had been cut, have grown fairly tall, and they're crowded together enough to where it pretty much closes the forest floor from much sunlight. And so a canopy is basically the roof of the forest where the interlocking trees and their leaves form a barrier to the sky. Now, of course, when we mean 100%, that means no light, but more or less it's shaded the vast majority of time, no matter where you go in this 20-acre area. Stand 2 is 85 years old. It's about, is significantly older, 35 years older, and is only 80% closed, with a mixture of mid-story, which means middle-level trees, but we're starting to get some understory grasses, which tends to happen once some trees start dying off and the canopy opens up a bit and some sunlight can penetrate the forest floor. So, not surprisingly, if a canopy of trees is not totally open and totally shading out, you'll start seeing more grassy, small plants on the ground. Stand 3 is even older. It's 115 years old and had a 60% closed canopy and extensive grassy forest floor. The team wanted to see what type of habitat was more favorable to the birds. So, as you can see, we have 3 stands that kind of have this not only an age gradient, but going along with that age gradient from 50 to 85 to 150 years, the character of the treetops is different. But in this part of the country, most tree stands that are 50 years old are fairly dense if they've just been allowed to grow up as is, and so it tends to be pretty shady, what we would call a closed canopy. As they get older, trees die here and there for a variety of reasons, and so the canopy isn't quite so closed, and this continues as the trees stand continues to age. Different species of birds tend to prefer different habitats. Some like closed forests, some like open meadows, some like a mix. It depends on the species. Let's see what the data says about these purple wamplers and if there is a particular type of habitat in a forest that they may seem to prefer more than others. We can garner this by how many birds were counted each day over this 13-day period. Let's take a look at the results. So, here's the data that was gathered over the period of 13 days by the team. So obviously we had some people working in each stand during this time period. And these were the count of the number of purple wamplers that they see during the day in the stand that they were assigned to. And we look at the data here, and you can probably get a visual sense of sort of an idea of preference, but sort of doesn't really cut it. What we want to do is start taking this data and analyzing it in a way to really get a clear picture of what we've got here. Now, you're probably thinking one of the most obvious things we can do is add up each column and then divide by the number of values that are in each set, and we have what's known as the mean average. And there's absolutely nothing wrong with making that part of your statistics, but really it's only the beginning. And over this quarter, we'll be looking at how to take a data set like this and take that fundamental mean average and start seeing what we really can do with it to tell a richer and clearer picture of what our experiment is trying to tell us. But before we do that, let's try to take a minute and break down what were the scientific method steps that were followed here. So what we're going to do is we're going to recap the actual experiment that we've been discussing, and we're going to take a pause in the video. We're going to take a minute for you to try to figure out what was the question, what was the hypothesis, the independent variable, the dependent variable. Is there a control group specifically? Sometimes there is, sometimes there isn't. What were the controls? How were these different sets basically kept the same in a way that made this experiment fair? You should have several of those. And what is the data that we're drawing from this in our dependent variable? And then finally, what is our conclusions can we draw once we've taken a look at the data? And what are some ways that we can improve this experiment? And we are always trying to improve our experiment. So let's pause the video for a second and then come back and tell me what were the following elements to this particular experiment. What was the question that was being asked? What was the hypothesis? What was the independent variable? The dependent variable? Is there a true control group? Remember, not always is there going to be one. If not, what would have made a good one, or is there a purpose to? What were some controls? And we're going to hold off on interpreting the data, but we'll go ahead and follow that the data set that we have right here and go ahead and take our mean averages so we can at least have a little bit of discussion. So let's take a pause here and try to identify these elements of the experiment. And then when we come back, we'll see how you did.